So I know so many of you. Try to see who I don't know. Anyway, I'm Shafi. I'm the director of the Science Institute, and for those of you who don't know, we are a collaborative center for research in theoretical computer science, and we were founded I guess many years ago at this point, in 2012, with a large grant from Simon's Foundation. It was also kind enough to renew our center, so we will be going strong for another 15 years at least, hopefully more. And the workshop on the complexity thing told the organizers, who are you? Introduce yourselves. Rubad is one of them. Yeah. And Rafael, where is he? Sure. I think it's another one. And and who's arriving, I think, a little later today after she's finished. So I want to go through a few logistics. We're going to put in the breaks. You're not supposed to take it in, or don't put it in. And some of them for drinks. I think you can take water in. There are lockers on the side of the building, which you can use. Omid is the videographer, and you know, whenever there's a problem, you sort of flag him down. He's very attentive, so he knows. And I want to thank Elizabeth Ren, who's the organizer for this workshop and is in charge for all the logistics for today's events. And we will have a reception at the end of the day today, so it's also customary the first week. Thank you very much. And I think that the next Abhishek is coming in. Or you're going to have another, we have a hierarchy. There's the director, and then the program organizer, and there's the speaker.
Thank you, Sophie. I haven't slept for this. So, welcome everybody to this program on minimal complex assumptions for cryptography. As you know, this is part of the Meta Complexity program that is ending with this workshop. And I'm really excited to have you all here. We have a fantastic schedule of talks, all at the intersection of cryptography, complexity, and basically ever since I started with cryptography, I kind of felt that right now is a golden area of work between cryptography and complexity. But right now I feel it even more. There's been so many breakthroughs in the last 5 years, and we're going to hear about all of these results here. So very excited that you all are here, and welcome. All right. Sorry. I should also introduce Abhishek, who's going to tell us about one of the biggest breakthrough results in the last few years, in particular about how to construct SNARK based on standard assumptions. So I'm very excited to have Abhishek tell us about cryptographic proofs in general.
Yeah, thanks everyone for coming this morning. So yeah, so this is going to be a general talk on cryptographic proofs, but the primary focus is going to be on succinct proofs. And I'll try to set up stage for many of the talks that will happen later today and some of them tomorrow. Okay, so allow me to indulge. Let's talk about proofs in general, right? So for most of us, our first memory of proofs is mathematical proofs, where there is a prover who's trying to prove some statement to a verifier. And usually such a proof consists of a bunch of lines, and each line follows via some rules or axioms. And the nice thing is that the proof can be just sent by a single message to the verifier, who can then decide to accept or reject. And such proofs have existed long before any of us were born. In computer science, we take a computational. In computer science, we take a computational lens to proofs. So the verifier is a polynomial time machine. And if you think about the class NP, then essentially says that for any true statement, there is an accepting proof, namely the NP witness that the prover can send to the verifier, who can then decide to accept or reject. And there is a second property, which is soundness, which basically says that if the statement is false, then any proof will be rejected, right? Any proof sent by the prover. So this latter property is what really speaks to the core appeal of proofs, which is that I don't really have to, take people's assertions on faith. I can instead ask them to prove it to me, right? And to utilize this power of proofs in the real world, Cryptographic proofs ask for much, much more. So two seemingly fantastical properties which seem impossible to realize at first, but nevertheless can be achieved. And I'm going to talk about both of these properties one by one. So let me take an example. So suppose a prover wants to prove to a verifier that a huge graph is 3-colorable. And since this is an NP statement, the prover can simply write down the entire coloring of the graph and send it to the verifier. But this is a very large proof, right? The witness here can be very, very large. And what we ask is if it is possible to somehow shrink this witness into a very, very small proof that can still convince the verifier. So this is the property of succinctness, which basically says that the proof should both be very short to communicate and very, very fast to verifier, much, much smaller than the witness size. And in this setting where the prover just sends a single message to the verifier, these are referred to as succinct non-interactive arguments. So succinct because the proof is short, non-interactive because it's one message, and argument because the soundness guarantee is only against polynomial time provers or computational soundness. And these proofs have lots of applications. The general idea is that they allow us to do verifiable delegation of computation. Namely, a weak computational device can offload some heavy work, let's say training some neural network, to a cloud server, and then ask the cloud server to actually provide a proof of correct computation. And because the proof is short and easy to verify, the verifier can quickly check the answer. Okay. So that's the first property. The second property of cryptographic proofs that we care about is where the prover does not even want to reveal, let's say, the coloring of the graph to the verifier. Instead, it wants to send a proof that hides the witness from the verifier. And this is called zero knowledge, something we have studied for many years. Essentially says that a proof can convince a verifier that a statement is true without revealing why it is true. Again, in the non-interactive setting, we refer to it as non-interactive zero knowledge. And non-interactive zero knowledge is very useful for privacy applications. So here is a flagship application these days. Let's say I have a blockchain, which is essentially a sequence of transactions ordered in blocks, and I want to hide everything about the blockchain. So I want to hide all the transactions, the account balances, and everything. So how could I go about doing this? So let's say I have a way of encrypting everything. But now the problem is that how do I verify that a transaction is valid, right? So maybe somebody's account balance is actually 0, but they want to try and do a transaction which exceeds their account balance. So using zero knowledge proofs, we can solve this dilemma by just asking the person conducting the transaction to prove that they have sufficient balance in their account. And this is a general idea of basically forcing honest behavior on participants while preserving privacy of data. And for this reason, proofs have lots of applications in the real world. Over the last several years, perhaps we most know about the applications to blockchains, many companies using these proof systems. But even traditional things like signature schemes have, or perhaps the most widely used signature schemes have their roots in interactive proofs. Proofs also have strong connections to theory. So we know of strong connections to complexity theory like PCP theorem, IP=P space, and connections to other areas as well, which I think some of these things will be covered later on in this workshop. Some other connections which are maybe subcases of connections to complexity theory. So we will probably hear about some connections to meta complexity, maybe tomorrow or day after. And also connections to de-randomization as well. These are pretty old connections, but some newer connections have been established, which are kind of exciting. Okay, so now having said all of this, let me ask the basic question: do cryptographic proofs exist with these properties? And if I allow for interaction between the prover and the verifier, namely that they can exchange a lot of messages with each other, the answer is yes, and we have known this for many years. In fact, we can build interactive proofs both with zero knowledge and succinctness properties from fairly weak assumptions. So for this talk, the main focus is going to be on cryptographic proofs that are non-interactive. And in this particular scenario, for the case of NISX, the answer is again yes, something that we have known for a while, although a lot of progress has happened recently. And for SNARKs, the answer is a bit complicated. So I'm going to elaborate on this part primarily for the rest of the talk. And again, just to mention, even though the answer for NISX was yes and was known for many years, a lot of progress has happened in improving our understanding of this field in the recent years. So in this talk, I want to survey some of the recent research in the case of SNARKs. And along the way, I'll also establish connections, how this line of research also has implications to NISX. Let me now formally define succinct non-interactive arguments. So let's say there is a prover that wants to prove that the output of some deterministic or non-deterministic computation is 1. And we want the following properties from such a proof. So first of all, I'm going to allow the prover and verifier to actually share some common reference string that has been sampled in advance honestly and given to both the prover and verifier. And now in this model, I want first and foremost succinctness, which says that the proof size, the verification time, and CRS size, ideally all of these things should be very small, much smaller than t, where t is the time of computation. And soundness, basically, as before, just says that if the statement is false, namely the output is not equal to 1, then the proof should be rejected. How do we build SNARKs? How can we build SNARKs? What do we know in this area? So turns out we know a lot. This is something that people have been studying for many years. I'm out of space here on the slide. So incredible line of research. And some of these results actually can even build SNARKs for NP. So really, what we would like, have tremendous real world impact, something that I've already conveyed. The main issue is that the results that do actually achieve SNARKs for NP, and in fact, even other results, security-wise, they are lacking. So the main issue is that these results either achieve heuristic security in idealized models, or rely on what are called non-falsifiable assumptions. I'm not going to elaborate right now what non-falsifiable assumptions mean, but just very briefly, just think of them as assumptions where it's not efficient to verify if somebody has actually found a break for the assumption. Okay, so can we then build SNARKs from actual standard assumptions? So this is what has happened in the last few years. So until 2019, we really didn't know anything in this space. And then 2019 onwards, things started to change, starting from the work of Kalai, Panath, and Yang, who gave a construction for SNARKs for some classes of languages, which I'll mention in a moment, from not from falsifiable, but still non-standard assumptions. And then things started exploding in 2021, where many constructions were proposed. And this is only continuing in the last 2 years or so. So all of these results focus not on NP, but on either deterministic computations or some subclasses of NP. And when I say standard assumptions, I really mean assumptions like, that we love in cryptography, like learning with errors, standard assumptions over bilinear maps, Diffie-Hellman assumptions, and so on. Another thing to note is that I've ignored here some lines of research, which maybe will be covered later in the workshop. Things like privately verifiable SNARKs, where we don't actually require that anyone can verify a proof, but rather only designated verifiers can verify proofs. Okay, so now let me get into technical details of how some of these works actually achieve these results. Okay, so let's start with a general recipe for SNARKs. And this recipe, by the way, is not limited to these works. This is actually true for pretty much all SNARK constructions that we know in the literature, even the practical constructions that are used in the real world. So a very simplified view of things. So we start with the proofs in some Oracle models. So think of, for example, PCPs, where the prover establishes some giant Oracle, which is not counted in the communication. And the proof size, we only think about the proof size as the verifier queries to these oracles. Okay. Then we try to somehow transform these Oracle model proofs to succinct interactive proofs where there are no more oracles, and the prover and verifier are allowed to interact with each other, exchange multiple messages, and then we try to compress them into a single message proof. So the first step involves building some cryptographic compiler to get rid of the oracles, and the second step is a round compression step, which requires basically collapsing all the rounds of the protocol into a single message. So I'm going to focus on the second part here for the rest of the talk, which is where these two lines of research, the applied results and the theory results, they diverge primarily in the round compression step.
So when you go from the oracle to the interactive, I should think in my mind like the Sylvia type CS proofs.
You should think of exactly like Killian style proofs where you use some kind of commitment scheme maybe to commit to the PCP in a succinct form.
Killian talked about a short, we didn't talk about it. Okay.
No, so what I'm saying is think of Oracle as a PCP.
PCP.
Yes. Okay. Yeah. Okay. Good. So let's talk about round compression of interactive proofs. So we want to start with some proof which is interactive and end up with a non-interactive proof. And ideally, we would like this transformation to preserve the properties of the interactive proofs. Namely, if we start with a proof that is succinct, we end up with a snark. And if we start with a proof which is zero knowledge, we end up with a NISIC. Okay. And there is one transform that we have studied for many years, which actually satisfies these properties, namely the Fiat-Shamir transform. So this transform basically says the following: if you start with some interactive proof, in this case, just a 3-round proof, but it could be multiple rounds, where the verifier's messages are just random strings, then we can actually transform it into a non-interactive proof by just computing the verifier challenges using a hash function. And the Fiat-Shamir transform says that if we model this hash function as some idle object, a random oracle, then this resulting protocol is actually still secure, in the sense that soundness of the underlying protocol, the interactive protocol, is guaranteed in the non-interactive setting as well. So what do we know about the security of Fiat-Shamir transform? So heuristically, this is secure, in the sense that we just imagine that the hash function behaves like a random function, and then we can say that okay, this is hopefully secure. But in theory, we know that this is not a secure transform, in the sense that people have shown, starting from the work of Barak and then Shafi and Yael, people have shown that there exist protocols for which there is no way to come up with a secure hash function such that the resulting, the final non-interactive protocol will actually be secure or will be sound. So this is where basically things have changed in the last several years, which is trying to circumvent these negative results. How to actually, how to securely instantiate the Fiat-Shamir transform using standard assumptions, or how to avoid these impossibility results. So the idea is essentially the following. I'm simplifying things, but let me just state what are the crucial steps involved in trying to get results in the standard model. So the first step is to avoid these impossibility results by focusing on a subclass of interactive proofs, namely proofs which are statistically sound. Okay. So that is unbounded time prover can also not cheat. And then in the second step, we build hash functions that essentially avoid the bad challenges which might allow a cheating prover to prove false statements. So if you think about statistically sound proofs, we have the guarantee that for every first message, let's say alpha here, there are only some small number of verified challenges for which there exist accepting third messages. So the idea then is to build hash functions that can somehow avoid these bad challenges. And these are what are called correlation intractable hash functions. In the last 5 years, this idea of compiling a subclass of interactive proofs into non-interactive proofs using correlation intractable hash has found lots and lots of applications. So this is where the research on snarks and NISICs have, they join, in the sense that using this paradigm, not only have we managed to build snarks for deterministic computations and other subclasses of NP, but also NISIX, establish hardness results for PPAD, build other objects as well. For example, verifiable delay functions and even counter examples to parallel composition of zero knowledge proofs. Okay, so very, very successful line of research. Okay, so what I want to focus on is how to use this idea of correlation interactability to build snarks, and also just comment a little bit on how it also applies to NISIX. So let's actually start with the latter. So if we want to use this idea to build NISIX, then what we want to do is start from a interactive proof, which is statistically sound and has zero knowledge property, and then build some kind of correlation interactable hash functions which can avoid the bad challenges in that particular interactive proof. And turns out that in the case of zero knowledge, the first step, which is building an interactive proof, this is easy. This is something we have known for many years. So really the hard part is actually in building correlation interactable hash. So how do we build correlation interactable hash? This is essentially what we now know from many works in the last 4 or 5 years. We know actually correlation interactable hash for some kinds of relations, which I'm not going to dive into right now, from both standard lattice assumptions and also from standard group assumptions. And this is going to be the focus of the next talk, so I'm not going to get into this now. What I do want to talk about is how this general paradigm can be used for building snarks. So here we want to start from interactive proofs which are succinct, and then apply this correlation interactable hash framework to that. So here the pressure point actually already shows up in the first step, which is actually building succinct proofs which are statistically sound. So let's just assume that we have correlation interactable hash for whatever relations we need and we care about. Let's just focus on the first step, which is actually building succinct interactive proofs which have statistical soundness. So the main reason why this step turns out to be challenging is because of this simple barrier, which is we want interactive proofs both with low communication and statistical soundness. And this is something that we know for some subclass of computations like bounded depth or bounded space deterministic computations. But beyond that, they are unlikely to exist. And this creates the main barrier in trying to apply this general methodology to build snarks for let's say P or other subclasses of NP. So here is the blueprint for trying to overcome this barrier that I'm going to elaborate in the next few minutes. So first of all, I'm going to change the problem statement a little bit. Instead of talking about, let's say, deterministic computations, I'm going to talk about a particular class of languages called batch NP. And I'm going to explain in a moment what that means. So we are going to first shift our focus to building snarks for batch NP. And for this class of language, I'm going to introduce a new soundness notion, which will help us in overcoming this statistical soundness barrier. So it will help us in transforming interactive proofs for batch NP using the correlation interactable hash framework to build snarks for batch NP. So then once we have this in place, then I'm going to show you that batch NP proofs or proofs for batch NP are sort of complete in the sense that once you have snarks for batch NP, you can actually build snarks for deterministic computations. Okay, so this is the second idea. And then the third question, remaining one, is how do we actually build these interactive succinct proofs for batch NP? And this is the last part, the last piece of the puzzle. Okay, so once you have all of these ideas together, you can obtain snarks for all deterministic computations. And as a bonus, you get snarks for batch NP. Right, so this is the blueprint. Okay, so let's talk about snarks for batch NP first. So the problem statement is as follows. So the prover now, instead of proving one statement to the verifier, it has, let's say, capital T statements, and it wants to prove that all of them are true. So this is a conjunction over T statements, T NP statements. And the key requirement is that the proof size should be small in the sense that it should not grow with the number of statements, right? But it is allowed to grow, let's say, with the size of a single witness. So it's really amortization, right? That I can prove capital T statements by only paying in the size of one witness. That's it. This notion of batch NP has been studied before in the context of batching, in the context of signatures, in the context of interactive proofs, and it has lots of applications. In fact, perhaps one of the most common applications of snarks in blockchains which is rollups, can be captured by this idea of batch NP. Okay, so now let's go towards identifying the right notion of soundness for batch NP. So how do we build snarks for batch NP? So we have the following options. I'm just reiterating some of the points from earlier. So one option would be to go towards succinct interactive proofs for batch NP, where proof means statistically sound. So we know that if we have statistical soundness, it is friendly to the Fiat-Chemie paradigm using the correlation interactability hash framework. But the problem is we don't know how to build, we don't know any constructions of succinct interactive proofs with statistical soundness for batch NP. And the alternative would be to go towards computationally sound interactive proofs for batch NP. And here we do know such proofs that they exist, in fact, even for NP. Yeah.
So we do know how to build succinct proofs for batch NP, like using the IP equals B space theory. So what would happen? I mean, that's not an efficient prover in any sense.
Yeah.
Does that mean anything for your?
Yeah, I mean, inefficient provers. I'm not sure. I haven't really thought about what that would mean in this setting, but.
You have an argument where the honest prover is inefficient, and you're talking about sounds for efficient provers, sort of meaningless, right?
Yeah. Okay, so yeah, so in the case of succinct interactive arguments for batch NP, we do have candidates. Killian's seminal work gives us such arguments for all of NP. In fact, forget batch NP. The problem is that Killian's protocol it's not quite instantiable securely, and this is something we know from recent works. So to avoid this conundrum, the idea that I'm going to describe basically tries to interpolate between statistical soundness and computational soundness. And again, for cryptographers here, the notion should be very intuitive. So the idea is to use a notion of somewhere statistical soundness. And the idea is very simple. So we are in the setting where the prover is trying to prove capital T statements to the verifier, right? That all of them are true. And what we require is that instead of insisting statistical soundness for all of the capital T positions, we are only going to require that there is a position I where this position I is hidden somehow in the CRS. The CRS encodes I and it hides I. And we are going to require that at this position I, a cheating prover, even unbounded cheating prover, cannot prove a false statement. For the other positions, I don't care.
Are we supposed to be thinking of 3-round proofs for now?
No, I mean, the idea is, yeah, it will work for more rounds. Yeah. I mean, I'm just using pictorially. I'm always talking about 3 rounds here, but yeah, it's not important. Yeah.
Saying that you want us to focus on a particular location?
Yes. So I'm only going to require that at a particular location I, which is unknown to the prover, it's embedded in the CRS and hidden. At that particular location, even an unbounded time prover cannot prove a false statement, right? For the other locations, I really don't care.
Computation.
Yes, it's going to be computationally hidden.
Unbounded prover could know this, but yeah.
But the other locations are requiring argument.
Yeah, I mean, intuitively, that's the kind of guarantee, but again, it's not important. I mean, the main point is that at location I have statistical soundness, right? Okay, so a few remarks. So first of all, if you think about the communication of the proof, right? This notion sort of makes sense because the proof is allowed to be as large as a one witness, right? I can hope for statistical soundness for one of the instances, right? So in that sense, It's compatible with the batch NP. And now, why is it useful in the context of the correlation intractability hash framework? The reason is very simple. So suppose the statement, this conjunction is false, right? So what that means is that there is at least one index I such that xi is false, right? And that's all I care about, right? Because now if I start with an interactive proof where I have statistical soundness for that location for xi, right? Where I manage to ensure that statistical soundness holds for the ith index, then I know that I have statistical soundness for xi, right? And therefore, when I try to, this statistical soundness for just xi is all I need, right? In order to actually do the round collapsing using correlation intractability.
So are you thinking about the prover as computationally bounded here?
I mean, in the final one, it is obviously computationally bounded. Yeah.
So the prover cannot distinguish what xi is.
What I is.
What I is,
Yeah.
right?
And the size being the witness size dependence will not matter.
No, that I'm allowed actually, right? So I'm not actually aiming for succinctness like NP, where the proof should be smaller than one witness. I'm allowing the proof to grow with the size of one witness. That's the main thing in batch NP. Yeah.
The CRS depends on I. In fact, it encodes I, but it doesn't depend on X.
No, it doesn't depend on X. Yeah. It only depends on.
And you will talk about how to build such SSS?
I am going to talk about it. Yes.
So is the idea of the proof of security that you're just going to ask for the proof a lot of times and extract all I?
Extract all sorry, for every location? No, I don't actually need to extract for every location. The point is that, again, right, for soundness, I only care about the fact that, if one of the statements is false, right, I only want to get a contradiction, for that.
I see.
Right.
And some we're going to bootstrap when carrying that they're all eventually, or not.
No, I don't actually care about that.
Okay.
For contradiction, I only care about, showing that, one of the statements is false. That's good enough, right? We are in the conjunction setting. So yeah, it's not the or setting. Okay. So now let's talk about the second step. So let's imagine that we already have SNOCs for batch NP. Okay. And now let's see how we can use SNOCs for batch NP to build SNOCs for P. So again, by completeness, I don't mean complete for NP. I really mean complete for deterministic computations. Okay. So here also the idea is very, very simple. So let's just think of a deterministic computation written down as follows. So all of these columns here are just the states of the Turing machine. So you start with some input and you transition through all these states and eventually you stop. Right. So I can just rewrite this in the following way. I can write down capital T NP statements where each statement simply says that the transition from the first state to the second state is correct, the transition from the second state to the third state is correct, and so on. Right. And now I can just try to use a SNOC for batch NP to actually build a SNOC for deterministic computations. So that's kind of the high level blueprint, but there are obviously several issues that show up. Yeah.
Like, why do you call it complete?
Yeah, so again, complete for deterministic computations.
It does batch proof for, say, does a SNOC for deterministic computation implies SNOC for batch NP?
No, sorry, what I mean, yeah, maybe I'm misusing the word, but what I mean is that SNOCs for batch NP implies SNOCs for P. Yeah, that's what I mean. Okay, so yeah, so that's a high level blueprint, but there are several issues here which I'm going to just mention but hide under the rug. So the first is that you can notice that in general these statements themselves are quite large, right? These states, they could be quite large, and therefore even the batch NP statements here can be quite large. So we can use cryptography to actually shrink them. So just think of hashing, and using appropriate hashing, there is a way to shrink all of these statements. In fact, I don't even want to communicate all of these statements to the verifier, right? I want to build SNOC for P. I can't communicate T statements.
I want to understand something. Just this statement. If you have SNARKs for batch and P, then you have SNARKs for P of what size?
Good. So here, so if let's say I write a T time computation, the snark for T time computation will be roughly polylog in T and then security parameter.
Okay, unrelated to the space.
Yeah, exactly. So that's the point that I was actually trying to.
That's before. Okay, you're saying before the obvious thing, so to speak, would be space.
Yes, exactly. Yeah,
And
exactly. Yeah. So to get rid of the space dependence, we can hash these states, right? And then I don't even want to communicate all of these T things to the verifier. So there's an additional animation missing here. Imagine a hashing across these T statements as well to just one hash digest. Okay. So that way, so again, there is some cryptography involved here, which allows us to shrink everything. And
Excuse me, but you call these NPs, what's the witness here? These are deterministic steps.
Yeah.
ST1 to ST2.
Yeah.
So you write T NP statement?
Yeah, I mean, you can just think of, the way they actually become NP statements is, the state basically becomes a witness. Yeah, once I do the hashing, the state actually becomes the witness. Yeah. Yeah.
So you say each of the statement is a hash of the state I to hash of state I plus one.
So eventually there's just going to be one hash, right? And then, the witness will be, the state and, imagine a path in the Merkle tree or something like
So
that.
what's the key point that differentiates this case from snark for MD?
Good. Good. So yeah, so the second thing that is missing, I'll answer your question in a second. So the other thing that is missing here is that in batch NP, right, the T statements, they don't have any relationship to each other, right? They are just T arbitrary statements, right? And there's no requirement that there is some consistency or some tying together of the statements. But here we do actually care about that, right? It's important that this ST2 is the same as this ST2 and that ST3 is the same as this one here. Yeah.
So also you were saying that now the witness size for a single statement is actually pretty large. But you are saying that if I look at a statement, then the size of the proof is equal to the witness size of one.
Yeah, so good. So now you're asking great questions, which I did not want to answer. But yeah, there is a way to deal with that also by shifting to the RAM model, and we can all of these things can be addressed there. Yeah. Okay. But yeah, coming back to this point that we need to make sure that these statements are actually tied together, right? So ST2 is the same in both of these instances, right, and so on. So again, for that also we use cryptography, and we use hashing, which allows us to do this tying together of the statements. And this is where Rachel, your question kind of shows up. So this does work for P in the sense that we can ensure that this consistency actually works across each of these statements. In the case of deterministic computation, there is an efficient way to check this. For general NP, this step just falls apart. We don't know how to think of it as this way, right? What is happening here when I try to tie these statements together? Prior to tying them together, all I have is sort of local soundness, right? I'm saying, okay, this step is sound separately, this step is sound separately, and so on. But there is no notion of global soundness, right? And this problem is not unique to this particular approach. This has shown up even in prior works in the setting of private verification. And we know how to solve this problem for deterministic computations, but for non-deterministic computations, the stitching together of local soundness to global soundness just doesn't work. Yeah, so again, I'm just saying that in the case of P, actually in the reduction, I can actually just check everything in polynomial time. It's a T time, it's a polynomial time computation. I can just check everything. Yeah, and otherwise, yeah, so that's really the crux of the issue. Again, technical barrier or fundamental barrier. Yeah.
The attacker knows to stay too. Other reduction knows to stay too.
And yeah, I wanted to say some more things, but maybe I'll skip. Okay, so then finally, let's go to the third step, which is actually how to build these somewhere statistically sound interactive proofs for batch NP. So the construction that I'm going to show you, again, skipping a lot of details, but the high-level blueprint is very similar to Killian's protocol, for those who are familiar with Killian's protocol. So the idea is as follows. So the prover wants to prove T statements, right? Conjunction of T statements. So what he's going to do is write down a PCP for each of the T statements. Okay. So PCPs are written in this row-wise fashion, and we have T rows. Okay. And now we are going to hash these.
Just so we remember, there exists some state such that.
So now I'm just talking about batch and P, so you can even forget that that translation. So you can just think of them as general statements.
So now we are in not
Batch
an
and P.
argument
In the interactive setting. Good. Yeah. Sorry. Yeah, I forgot that transition. Yeah. So now that we have argued informally that snarks for batch and P imply snarks for P, I'm now going back to batch and P and focusing on how do we build interactive proofs for batch and P with this somewhere statistical soundness and the right amount of compression, right amount of succinctness. So I'm just focusing on that step, right? So you don't need to think about how these statements xi look like, right? Okay. So again, we have these T PCPs, and we are going to hash them in a particular way. So the hashing is going to be actually column-wise. So for example, the first hash, which is a small digest, is going to encode essentially the first bit of all the T PCPs. Okay. And similarly, the second digest encodes the second bit of all the PCPs and so on. Okay. So roughly the number of hash digests that I have is just proportional to the size of one PCP. And this is communication I'm okay with for now, right?
This is just a regular hash, like no special.
So this is going to be a special hash, but yeah, I'll just mention briefly in what way it is special. Okay. So the prover now sends all of these digests to the verifier. So the verifier is now, just as in Killian's protocol, send PCP queries. And in fact, these queries are going to be the same for all of these PCPs. Okay. And now, as a first step, the prover is just going to open these columns. Okay. So forget about communication for now. Let's just focus on soundness. So I want to achieve this notion of somewhere statistical soundness. And for that, what I want to do is ensure that these hash digests, so there are T of them, can somehow together encode one witness, right? Some witness corresponding to the ith statement. And the way I will do that is by using these, the hash function that I will use will have this property that it can also be programmed on an index I. And now once I program the hash key on index I, it will ensure that each of these digests encodes the ith bit of each hash. So by encoding the ith bit of each hash or the input to each hash, it ensures that basically an entire PCP is encoded.
You separately encode the whole column using computational collision resistance and whatever.
Yeah.
And then one of the rows.
Yeah, so I'm encoding exactly just one of the rows. And this again, for cryptographers, this is what is called somewhere statistically binding hash, which again, very similar notion to, or rather the motivation for somewhere statistical soundness.
So something about the arrows here about who's the judge here?
The verifier. Yeah.
Okay, so that's about the age. Right. Another thing is, so I want to think about each one of these columns as a tree, as a normal tree.
Sure. Yeah,
Yeah.
you can think about
And
that.
I want to cross them to think that there's this
Yes.
response to the PCP for XI.
Yeah, so again, exactly. So the first digest, sorry, going back, right? The first digest is encoding the first bit of all the PCPs.
Right.
The second digest is encoding the second bit of all the PCPs and so on. And now the way I'm going to do program one PCP in these digests is by using a hash function where, once I program the key of the hash on bit I, what it means that in each of these hashes, right, the ith bit of the input is programmed. It's statistically binding on the ith bit of the input, right? So the ith bit of the input to this hash is the first bit of the ith PCP, right? And similarly for this one also is it's the second bit of the ith PCP and so on, right? So this way I have encoded the entire ith PCP.
So can the hash function just output the ith bit and ignore the rest of the?
So that you're going to you're talking about the construction of SSB hash. I mean, you do need, some collision resistance, etc. Right?
On other nodes.
Yeah.
So maybe you said before, but when you say the word program, what do you mean? exactly?
Yeah, so program essentially just means that the key of the hash, right? It can encode a bit I, and and this bit I, the hash key hides the ith bit of the this bit I. And the idea is that once the key is programmed or it encodes a bit I, the guarantee is that you cannot produce two different inputs, let's say X and X prime, where they differ in the ith bit, but they have the same hash.
That guarantees statistical?
Yeah, that guarantees statistical. Exactly. Okay. So yeah, so achieving somewhere statistical soundness is easy, right? Once we use this template. So now let's talk about, so once we encode the ith PCP, then we have statistical soundness for the location I. So now let's talk about communication and verification time. So far I said that in response to the PCP queries, the prover just opens these columns, right? But look at the size of these columns, right? Each column is of size t. So as such, this proof is not really succinct so far, right? Because the opening is too big, right? We want to be sublinear in T. Okay, so let's just look at these columns actually, right? So essentially, each of these columns, I can just think of what the verify does here, right? It's basically going to run the PCP verification for the first PCP, the second PCP, and so on, right? So I can just imagine, each of these verification steps as just, a new batch of NP statements, right? And if I just imagine them as a batch of new NP statements, then I can just try to, run a batch NP proof again. That is, instead of asking the verifier to actually verify this, I will just ask the prover to give me a new batch NP proof, right? And recurse, right? So that would be no, these are just individual PCP verifications, right? Yeah, that tying together we already did in the transformation from batch NP to P. Here we don't need to worry about it. Yeah.
We started with the batch verification program where we have capital T statements.
Yeah.
When you are recursing, don't you still have capital T?
Yeah, good. So yeah, exactly. So the problem is that, yeah, we started, if we think about this recursion, right? We started with T statements. But then in this, this delegation step, right, I again have T statements, right? So this recursion is not really interesting yet, right? It will never end. I will always end up doing, batch NP for T statements. So yeah, so that's not interesting. So the key idea that, that happens in these works to achieve succinctness is a folding step. So the idea is that you actually somehow fold two statements into a single statement. And this basically allows you to compress T statements in the recursion step to basically T by 2 statements, right? And if you can actually do this folding of statements, then you can now keep on recursing, right? Because after then log steps, you will end up with the, in a case where you can just send everything as it is, right? So this folding of the statements is not something that we can do, trivially. But what is shown in prior works is that you can actually do this folding of statements if the statements have structure. And in general, you can always use cryptography to sort of, create this structure. So just as a simple example, if you think of the statements as just like literally just numbers, right? Which are, let's say 1, 2, 3, 4, and so on, right? To basically fold 1 and 2, I can just use a number, So sorry, to fold two statements, let's say 2i minus 1 and 2i, I can just use the number I, right? And from I, you can rederive 2i minus 1 and 2i, right? So it's a very trivial folding. And then there are additional steps, which again, I'm not getting into in this talk, which are involved in making sure that the verification time doesn't explode. But this is sort of the key idea, which allows you to achieve compression. Basically fold the statements into T statements into T by 2, then T by 2 into T by 4, and so on until the prover can actually send the proof in the clear.
So are these new statements? Are they when you sum them up, are they shorter than the original ones? Or?
So yeah, so the new so when I go to T by 2, right, I have to ensure that each statement is actually as big as a statement in the T case, right? Yeah, I don't just mean literal concatenation. Otherwise, yeah, I'm not going to achieve anything, right? So yeah, so that's why I was saying that this folding, the way I showed it in the picture, I mean, here there is really, I'm just concatenated them, but actually what happens is that, yeah, you compress them into, yeah.
And you
something
need
short.
the witnesses to be shorter too?
So
you go back from it, you have W2, like go one slide back, this
Yeah.
W1, W2, you don't need them to be this length of.
Yeah, so I mean, that also happens in the background, but yeah, I'm again hiding, yeah, all of this information. But yeah, that also happens, yeah. Good. So the way it actually is shown in these papers is that so first you define like a very particular language, okay, which we call batch index language. So there, this kind of folding is just there. The way the language is defined, it is literally the statements are just numbers, you know, and they're all connected to some hash, which is part of the NP relation circuit. Right. So their folding is kind of easy. The main difficult step is to ensure that the verifier's runtime doesn't explode. And then there is a general transformation from this particular language, which has this very nice structure for folding, to general NP statements. So it is general in that sense, right? That basically you can first consider a very particular language where the statements are structured, build a batch NP proof for that, and then you do a general transformation from that language to general NP.
Yeah, go with the W3 here. Oh,
yeah.
This should be W4.
Oh, yes. Yes. Sorry.
It's not
Okay, so this is, sorry.
So for these interactive proofs, do you need algebraic assumptions or can you get away with just?
So no, not really. I mean, for these interactive proofs, yes, yeah. Because we are using this hash functions. SSB hash. So there you will end up using either things like LWE or DDH, but you know, we don't know it from general assumptions, but yeah, all of the nice assumptions that we care about, yeah, we can do these things.
Is in the 2-to-1 folding, do you get statisticals? Like, is there
No, so again, it's the way I displayed it on the previous slide, it was a bit misleading. Again, we are not showing a folding step for general languages. We first consider a particular language where this folding is just straightforward. And then once we build proofs for this particular language, then we do a general transformation from SNARKs for batch NP for a particular batch NP language to SNARKs for general batch NP.
That specific language is the folding statistical, or is it?
Yeah, I mean, there the folding is Okay, so a few notes on efficiency. So asymptotically, these proofs are great. In fact, I think we will hear later in the workshop even proofs that have that are super small in the sense that there is not even a multiplicative dependence on the security parameter; it's additive. So rate 1 proofs. Concrete efficiency wise, these proofs are not so great. So there are few annoying things that show up in these constructions. This is also true for the recent NISC constructions. So first of all, the way we currently use CI hash and the current constructions of CI hash, they induce non-black box use of crypto. And also in terms of the actual underlying tools, the crypto tools that we use to build these objects, they're kind of heavy. So yeah, probably not a good thing to compare these proofs with the practical SNARK constructions that are currently used in the real world. So one thing that I did not really mention so far is that even though almost all the works that I presented in an earlier slide on SNARKs focus on this Fiat-Shamir and correlation interactability hash framework, there's one work which is an exception, which is a work of Waters and Wu. So they don't use Fiat-Shamir, no correlation interactability, no PCPs. They build batch proofs for batch NP using bilinear maps. And this is a very particular construction in that it really uses bilinear maps in a way that we don't know how to instantiate from any other assumptions. This is sort of, for those who are familiar, the ideas are similar to the non-interactive zero-knowledge proofs construction of Groth, Ostrovsky, and Sahai from bilinear maps. Yeah.
I'm not sure if I understand well the folding, but let me just ask if you could have done T2 1 folding, then you would have solved your problem without PCPs and recursion, right? You fold 2-1. If you could have just folded T2 1, you would be done, or I'm not understanding folding correctly.
Oh, so that is just, I mean, like it's unusual. You're saying like, why just 2? Why not fold more things?
Your whole thing is starting with T and compressing it to 1, right? Yes. And you're like, well, as a tool, I'll just easily, trivially compress 2 to 1. Why don't you build a tree and trivially compress T to 1?
No, but that is actually what is happening, right? It's just that we are doing it, level by level, right? So first we fold T to T by 2, right? Then, you delegate this to the prover. But now the next time you fold T by 2 to T by 4.
Right? Aren't you alternating steps? You do the folding, but that doesn't shrink the overall witness length does not.
Yeah.
That is shrunk by the PCP.
That's related to my previous question. I see. Good.
Okay, so yeah, how many minutes I have? Maybe 5-6 minutes or something.
8 minutes.
8 minutes. Okay, good. Yeah. Okay, so let's talk a little bit about SNOGs for NP, right? So far I only talked about SNOGs for P and some subclasses of NP like batch NP. So what do we know in this regime in the context of standard assumptions? So first of all, we have this famous barrier to building SNOGs for NP from Jain-Wicks, which essentially says the following. So it says that if you want to try and build a SNOG for NP, where you want to reduce the soundness of the SNOG to some falsifiable assumption. Okay. So again, by falsifiable, I just mean that so this is the assumption that the challenger in the assumption is polynomial time. Okay. So Jain-Wicks says that this you can't really do using reductions that cannot decide the language. So it essentially says that you cannot build SNOGs for NP, or SNOGs for any NP language L using reductions where the reductions just don't run in time that is sufficient to decide the language itself. Okay. So this is, again, this is a simplified, my simplified view of Jain-Wicks. I'm not giving the formal statement here, right? But this is the takeaway of Jain-Wicks. And for those who care, there are some details here. So for example, Jain-Wicks talks about adaptive soundness, which means that the statement and the proof is chosen after looking at the CRS. So this is an important detail, but this is not the point that I want to focus on.
Do you have reason to, what do you think about non-adaptive? What is the
good? So in the non-adaptive case, the statement is chosen before the CRS.
I know what the definition is. What is what is your intuition about the law?
So Jain-Wicks doesn't say anything about it.
I know. What do you think? What?
So let me come to that. Okay, yeah. So what do we know about circumventing Jain-Wicks? So yeah, so some work that I did not mention earlier. So we do know from a work of Sahai Waters in 2013, which shows that you can actually build SNOGs for NP from IO, from indistinguishability obfuscation. I won't define indistinguishability obfuscation. You'll hear about it tomorrow. I think Rachel will talk about it. So there is a construction of SNOGs for NP from indistinguishability obfuscation. So a few points. So first to answer Iftakh's question. So this construction achieves non-adaptive soundness, right? So the statement is chosen before looking at the CRS. But more importantly, in terms of comparison with Jain-Wicks, this result as it is does not say anything about Jain-Wicks because IO is not a falsifiable assumption. Okay. But now, of course, you can say, well, if IO is not a falsifiable assumption, I can just instantiate IO with the latest and greatest results. So in fact, this is what we can do. So we can take this construction, instantiate the IO in Sahai Waters construction, let's say with the work of Ayush, Rachel, and Amit. And what we get is this following picture, right? So I'm just, instantiating now IO from a bunch of, falsifiable assumptions. So it's 3 or 4 assumptions, right? And now I can just look at, this combined thing as just one reduction, right? But what happens here is that what you actually get is snarks for this language L via a reduction R prime that actually decides the language. So remember, Gentrivik said that you can't actually build snarks for NP. Okay, again, adaptive, non-adaptive soundness aside, you cannot build snarks for NP using a reduction that cannot decide the language. And what Sahai Waters plus Jain and Sahai shows is that you can build snarks for NP, right, using a reduction that actually decides the language.
When you say the language, you mean the language being proved?
Yes.
If I consider, you're considering the static soundness where the statement is chosen by the cheating prover.
Yeah.
If you consider static soundness where I consider sequence of false statements and only prove the soundness with respect to that sequence, then IO is actually is actually a falsifiable assumption. Because you do know that for that sequence of statements, you are going towards the only thing that IO is not falsifiable is because the reduction will give a circuit which you don't know if those two.
Exactly. I really just meant it that way, right? So when I say IO is non-falsifiable, I just meant that in the definition, right? The challenger doesn't know that the circuits chosen by the adversary, but that they're equivalent.
Right. So if I focus on this notion of soundness, where I'm only looking at fixed statements, then this soundness is actually, IO actually shows you can build it from polynomial type falsifiable assumption. And that notion of soundness can actually prove the soundness where the statement is chosen by the prover, because just by a non-uniform security reduction, if there is a cheating prover that gives a distribution of X and can cheat, there always exists a sequence of false statements that they can cheat.
I see. So you are saying that you don't even need to do rely upon strong hardness assumptions in that case, just do a non-uniform reductions? Is that?
Yeah.
I see. Okay.
Yeah.
Yeah, that's interesting. Okay, but yeah, the point that I was trying to make here is that at least this the generic instantiation, if you do here, right, the assumption that you will end up using here will actually be quite strong in the sense that they will have to be strong against 2 to the witness length, adversaries running in that time. Because in essence, the point that I was trying to make here is that the core of Gentrivik's lower bound, right? The essence of Gentrivik's lower bound comes from the fact that the soundness notion of snark, right, is itself non-falsifiable notion, right? Because the challenger cannot figure out if the statement is true or false, right? And that's kind of what is crucially leveraged. When you build snark from IO, you basically transfer the non-falsifiability of the soundness definition in snarks to basically the non-falsifiability of IO definition. And now eventually you pay for it in the assumptions, right? When you instantiate the IO construction, you eventually pay for that by using assumptions that are quite strong. The interesting aspect though is that, one may think, well, why can't I then just do it all the time by just using a sufficiently strong assumptions, right? So let me mention that point a second. So the bottom line, combining all of these points is that you can build snarks for NP from quite strong assumptions, right? But with a large CRS that grows with the witness size, right? And this is the interesting thing about the IO construction, that even though you are using very strong assumptions, right, you're not paying for that in the size of the proof, right? Usually when you do, because in order to use such assumptions, you will be doing complexity leveraging, right? And intuitively, we should be paying for that in the proof size. But the nice thing about this construction, you don't pay for it in the proof size, you pay for it only in the CRS size. And that's the interesting aspect of it. And in some cases, for some languages, we showed last year that you can even shrink the CRS size. But one point that I want to make is that so far as far as I know, there is no non-IO approach to snarks for NP, right? This is essentially the only approach we know. And basically approved techniques are quite limited.
But are there midpoints so not all NP maybe, but some interesting languages for which you can do without IO, maybe something else?
I mean, again, so defining that interesting point, that's really the question. Because again, for things like batch NP or even bounded space NP, we can do it from standard assumptions without I/O.
Witness encryption is enough for slightly weaker notion of two-nested coding arguments. The mixed area applies. So witness encryption does.
Yeah. I mean, witness encryption has the same flavor as I/O, right?
So don't have any limits for adaptive security, non-adaptive security, right?
Yeah, as far as I know, we don't know of any formal lower bound, right? Yeah, this is where both directions sort of fail in the sense that the formal, we don't have any formal lower bound, but in terms of actually trying to build snark, techniques wise we are limited. We don't know how to exploit the non-adaptivity to actually build a snark.
Wouldn't falsify the possibility with I/O, which is a very efficient honest assumption.
Yeah, so you're saying that what if I actually show that gentrifix, extend gentrifix to the non-adaptive setting? So again, I don't think so because of the fact that the I/O construction, the difference in the reduction time, right? So
there's a natural family for which you believe. Just so asking you again.
Yeah, I mean these are all excellent questions. I'm happy to discuss them offline, but yeah, yeah, there are many things I still don't understand about this. Okay, so I think I'm out of time. Yeah. So yeah, I'll just maybe mention with one, open problems. The remaining I'll leave. But yeah, in terms of cryptographic proofs, the most natural open questions, snarks for NP from standard assumptions with small CRS. So it would be nice if we can build it from LWE, right, or some other single assumption, or even just new techniques for proving soundness. And in terms of NISX, which is not something I touched upon a lot, we do know now NISX from most of the assumptions we care about, like specific assumptions like learning with errors, DDH, all those sub-exponential DDH, bilinear maps, and many of the assumptions we care about. There are some things still missing, like for example, learning parity with noise and so on. But otherwise, we do know it from most of the assumptions we care about. But we don't know NISX for NP from general assumptions besides the original results on, I don't know, doubly or triply, whatever enhanced trapdoor permutations. But for example, we don't know NISX from any public encryptions, right? In fact, we don't even know whether NISX really are in Minicrypt or Cryptomania, but even this would be nice to, I think I'll just leave it at.
Now we have a half-hour break.